Okay, we're going to start again here. Here's an image of the surface of silicon. You see, showing the atoms. Are silicon atoms red like this? No. The red is just, whatever the computer decided to give the... What they're measuring is this is measuring electrical potential, voltage. This voltage they want to keep the same. And so the voltage is going to depend on how close you get to the atom, because the atom consists of electrons out here. Like, electrons are what charge? Negative charge. So if you have a probe here, it's going to sense that negative charge in the space around the nucleus. So we can see that here we got the silicon atoms, and this is a scanning, tunneling electron microscope image here. Dalton. Let's take a look. Oh, I'm sorry. Electric charges is chapter 2. Here. Like charges repel. This is neutral, nothing's happening. Opposite charges attract. These charges are influenced by magnetic fields. So when I say if you pass electrons through a magnet, they get deflected here. This is some physics, you don't have to worry about it, but charged particles will be deflected by magnetic fields and electric fields also. And so by using a magnet on a cathode ray tube, cathode rays are just these electrons passing through. You can deflect them. And the angle of deflection here depends on the mass to charge ratio. Things that are very light are easily deflected. Things that are heavy will have a lot more inertia and are more difficult to deflect. And so by looking at the angle of deflection, determine things. Here's the cathode ray tube here. Cathode ray tube, these are called electrodes here. You don't have to know the names of this. This is actually the cathode. The cathode is where the electrons are being generated. The anode is where the electrons are being attracted to. Cathode generates the electrons here, shoot out. There's a hole in the anode, so this just go pass through. This is a beam of electrons, the invisible cathode ray. Yeah. And this is, you just put an electric. You need a pretty high voltage, not just a simple battery like this, but you'll need a transformer to do it. And it depends on how much gas you have in here. If you have like 1 atmosphere of gas in here, then you need extremely high voltage, like tens of thousands of volts. Well, usually in a cathode ray, what you do is you get what's called a vacuum pump, and you suck out a lot of the gas. And so you only have very little gas. It's a vacuum, so it could implode. So be careful with that, because the pressure inside here is a lot less than the pressure outside here. And when you have a low pressure gas, then it's a lot easier to generate these beams of electrons. You only need about 5,000 volts or less to do it. But the mysterious cathode rays, they changed this material here, and then always got the same beam. And then you put a magnet in here, and you can deflect it. Beam. We have a cathode ray, but unfortunately it got cracked. Now the pressure inside the cathode ray's tube is 1 atmosphere, and we don't have enough voltage to generate the cathode rays. So we've got to get a replacement one. I'll check it again, make sure. Maybe I'll bring it in. This is called a electric field. An electric field, what you do is you put a positively charged metal plate here or a negatively charged metal plate here. And the way you charge it is by hooking it up to a battery, because batteries, push electrons one way and takes them out from another way. So there's a deficit of electrons on one end, we call that the positive end. The excess of electrons on the other end, which we call the negative plate. And so over here, the cathode rays were deflected towards the positive plate. It means the cathode rays are negatively charged. There's a magnetic field that deflected this way. Here's where they cancel out the electric field via magnetic field or vice versa. So they're undeflected. This is the Millikan oil drop. The apparatus is a lot different up in Griffith. They still have the same one. But they get a fine mist of oil drops here. This fine mist of oil drops falls due to what? Gravity. Gravitational force. And so these are just falling due to gravitational force. And then let's see, what we have is we have an electric field being generated by a battery. This is the symbol for a battery here. And so electrons are being sucked from this plate by the battery and being pushed onto this plate. And so this plate has a deficit of electrons, positively charged. This plate has an excess of electrons, it's negatively charged. It's easy to generate electric fields. Okay, then X. X stands for X-rays. And so what they do is they have at least what Millikan did was he had a radioactive source. This radioactive source, this is nuclear chemistry. Nuclear chem, you know, a lot of these atoms are unstable. And when these atoms break apart, they emit radiation. And X-rays are one type of radiation that these atoms can emit when they break apart. And X-rays are called ionizing radiation. You know, you're familiar with the process of ionization. What is ionization? Creating a charge, right? Creating ions. And so here, you know, ionization, we're taking, you know, neutral air and knocking electrons off. If you knock electrons off air, then you create charged species, ions. Right? And so, well, where do those electrons go? Well, those charged ions, they don't like losing that electron, so the electron can reattach to the charged ions, and then we got neutral nitrogen and oxygen molecules again. But some of those electrons might attach to a oil drop. And once these become charged, negatively charged oil drops are going to be attracted to which one? Which plate? The positive plate. And so you got gravity pulling it down, and you got electrical forces pulling it up. And they might balance out, cancel each other. If they cancel each other out, the oil drops just stay in one spot. They don't go down, they don't go up. They just float in space. Or they might get pulled up. They might get pulled down. And so based on this, he was able to determine the charge on electron. So X-rays and radioactive. And so radioactive, again, radioactive is nuclear chem. Nuclear chem follows a different set of rules. It has a different force, the nuclear force. And does everybody know what the nuclear force is? The nuclear force? No? You don't have to yet. We'll talk about it later. Chem 1B. In Chem 1B, that's when we're going to talk about nuclear forces in detail. But you do have to know something about nuclear force because there's something unusual about atoms, which we'll talk about in this chapter. There's some radioactive. Do you know when you have a radioactive atom, it's unstable. What's unstable about it? What's unstable about it is the nucleus. The nucleus of the atom's unstable, breaks apart, emits radiation. The types of radiation we get from radioactive atoms are gamma rays, high energy light, X-rays, high energy light, alpha particles. Alpha particles are a chunk of the nucleus that broke off, little chunk, 2 neutrons and 2 protons. Beta particles, you know, beta particles are also known as electrons. The electrons have a funky origin. You know where the electrons normally come from? The electrons normally come from this empty space here. But are there electrons in the nucleus? No. No, but do you know where beta particles come from? Beta particles are electrons that come from the nucleus. Now, how do electrons come from the nucleus? There's no electrons in the nucleus, right? And so that's very strange. Where do the electrons from the nucleus come from? Does somebody know? Probably not, because it's just weird. Not neutrons become negatively charged. You're right. It's because of neutrons. Do you know what happens to neutrons? Neutrons get transformed into protons and spit out an electron. It's a nuclear process. It's called a nuclear decay process, and that changes the neutron to proton ratio. You know, neutron to proton ratio is thought to be very important in terms of nuclear stability. For example, you get too many neutrons in there, it becomes unstable. And so one way to get rid of neutrons is by like beta emission, beta particle emission. But that's nuclear chem. We aren't dealing with nuclear chem in this, except for one case in chapter 2, which we'll talk about, and you should know it very well. But you know, a different set of rules. It's got to be a different set of rules, because what did I tell you? I told you that like charges repel. So if you got a bunch of electrons here, what do they want to do? That bunch of electrons, they're all the same charge. Don't you think they just want to scatter out in space? What's keeping the electrons confined to this region?
Attraction.
The attraction, the electrical attraction to
Positive charge.
the positive charge of the nucleus. The nucleus is where all the protons are, right? And so what's holding the electrons in the atom are the electrical forces of attraction between the electrons and the protons in the nucleus. Let's see, protons. This is the symbol I'm going to use for protons. This is the symbol we use for the electrons, right? But what holds the protons? Let's say I got 10 protons in the nucleus. What's holding the protons together? Because shouldn't the protons just scatter and be repelled from each other? But the protons are being held together. So I know what holds the electrons. What holds the electrons are the electrical forces. But what's holding the protons together so that they don't fly apart and scatter in every direction? Yes. All right. We'll just call it the nuclear force. How about that? Rather than the strong force. Well, anyway, the nuclear force, well, how does the nuclear force work? I mean, how does it keep a positive to a positive? Because the nuclear force must be strong. Why must it be strong? Because it has to fight against the electrical force. And so if there's a fight between nuclear force and electrical force, who wins? Nuclear. Because the nuclear force can keep 10 protons confined to a extremely small volume, right? And so in chemical reactions, do the nuclei change? You know, for example, in chemistry had its, I guess, origins in alchemy, and the alchemists were always trying to change lead into gold. They're trying to get the nucleus to change from the nucleus of lead into the nucleus of gold. In a chemical reaction, is that possible? No, impossible. Because in chemical reactions, you know, the atoms just get rearranged. They don't change or transform into other atoms. But anyway, I'm spending too much time on this, I think. And so this is all kind of review, right? So we got a lot of protons in there. And so what's holding, well, we just call it the nuclear force. How does the nuclear force work? I don't know. You know, the nuclear force is just holding it together. You know, that if you want to know how the nuclear force works, then you should understand the law of nuclear forces, or you should understand the theory of nuclear forces. What would you want to understand? What would give you? You need to understand nuclear theory, right? And nuclear theoreticians are trying to generate a fundamental picture of what's holding the protons together. One hypothesis is that the neutrons act as a kind of a glue that holds the protons together, right? Etc. So are we going to spend, no, we're not going to spend any time thinking about that. We're thinking about what holds the atoms together. What holds the atoms together? You know, what holds atoms together? That's what we care about because we want to know about bonds. Bonds hold the atoms together. Well, we just don't want to know about bonds because a bond is like a law. We want a deeper understanding. And so in order to get a deeper understanding, we want bonding theory, right, to better understand it. Bonding theory. Well, you know, it turns out that there is an underlying theory to chemistry. What is the underlying theory? Is it atomic theory in order to help us understand this? Well, we'll talk about it pretty soon. But anyway, this is mostly empty space with electrons and protons in the center there. How do we know this? This experiment. What's this experiment? The Rutherford. Rutherford shot these chunks of nucleus. How did he generate chunks of nuclei? These chunks of nuclei are called alpha particles. These alpha particles consist of 2 protons and 2 neutrons. And it was easy for him to generate because he just got some radioactive isotope, radioactive atom, and that radioactive atom naturally decayed, and pieces of it broke off, right, during this decay process. And those pieces that break off, now he can shoot through gold foil here. And so this is a small chunk of the nucleus called an alpha particle. It's actually +2. And they're very small. And so this is a plum pudding model. This is the nuclear atom model. And look at this alpha particle. It hit the nucleus and then bounced off. What caused it to bounce off?
2 positive charges.
2 positive charges. Positive charges repel each other. That's what caused it to bounce off, the repulsion between 2 positive charges. Here we can see mild repulsion here. Here we can see minimal repulsion because the repulsion falls off with the square of the distance. So you get a little far away, it's not going to be such a big repulsion. So here's our nuclear atom. Is this the structure? I don't know. Does this look like a pretty accurate representation? No. This is just some cartoon illustration. This looks pretty bad, actually, because there are a couple of problems with this. One of the problems is, okay, we know the charge on the electron, -1, and from Millikan, we could actually get that charge. Yeah. Here. The charge on the electron is -1.6 times 10 to the -19 coulombs. And so this -1 just means it's -1.6 times 10 to the -19 coulombs. Hey, can you have a charge that's -1.7 times 10 to the -19 coulombs? Let me ask you, true or false? In nature, a particle can have a charge of -1.7 times 10 to the -19 coulombs. A particle can have a charge of -1.7 times 10 to the -19 coulombs. Is that possible? No, it's not possible because you know the next charge that's allowed? -1.7 times 10 to the -19 coulombs is called a forbidden charge. The next allowed charge would be 3.2 times 10 to the -19 coulombs. Why? Because this is 1 electron, this is 2 electrons. Is it possible to have 1.1 electrons? slice a chunk of the electron off? No, unfortunately it isn't possible. And so what we see is this is called quantization of charge. You know, there's allowed charges and forbidden charges because you can't have part of a piece of an electron. And so it's going to be quantized as far as the next, what's the next allowed charge? Yeah, actually it's not, 4.8 times 10 to the minus 19 coulombs. And so this fundamental unit of charge is just n times -1, you know, where n is an integer. And so this is 1 fundamental unit of charge, 2 fundamental units of charge, 3 fundamental units of charge. Have you ever heard of a -1.1 charge on an electron? Never. Have you ever heard of a +1.4 charge on a proton? No, the protons are each +1 and the electrons are each -1. And so, well, it's kind of a hassle because we have it to 5 sig figs here. I don't want to write it to 5 sig figs. We'll just, and then this, you know, scientific notation thing. It's much easier just to call it -1. And so what we do is, this negative is the n. If we want the actual charge is n times whatever this is. And so we call this n. Okay, how much does a electron weigh? Electron weighs 9.1094 times 10 to the minus 28 kilograms, or grams, sorry. Times 10 to the minus 28 grams. So 9.1, we'll just call it 9.1 times 10 to the minus 28 grams for a single electron. And so let me ask you this. Is it possible to get 9.2 times 10 to the minus 28 grams worth of electrons? No. Did you know mass is quantized also? I can't just slice off a chunk of the electron. We don't think of mass as being quantized, you know. We normally when we weigh out something, we just weigh out however much we want or need, right? But in the case of electrons, we can't do that because it's going to jump. The next allowed mass for electrons would be what? 18.2. That means I could have 1 electron or 2 electrons, but I cannot have 1.5 electrons. And that concept is called quantization, you know, quantized. And those numbers are called quantum numbers. N is called a quantum number. And so we see quantum, quantization, in a lot of things, right, that are familiar. Well, what's missing in this chart? What's missing in this chart is the shape and the size of an electron. What is the size? How big is an electron? That's it. Nobody knows the size. You know, actually, some people know the size. You know how big an electron is? It's a 0 in size. How can an electron be 0 in size? It has 0 size. A lot of people just say electron is very, very small. But an electron is very, very tricky because, you know, this is what was the problem with the cartoon. They're representing an electron as a little ball, right? Is it possible to represent an electron as a little ball? No. Because electrons are very, very weird, and this has to do with something called quantum theory. You've heard of quantum theory before, or quantum physics, or quantum chemistry? Well, I told you that there's a theory that underlies chemistry, and the theory that underlies chemistry is called quantum mechanics, or quantum physics, or quantum chemistry. And all quantum is looking at the charge interactions in atoms, molecules, whatever else. And when we're thinking about the charge, well, you know, we got to know what is the shape of the electron, you know? How big is it? That way we can do some simple physics to figure out all the electrical interactions, right? But the electrons are very tricky because according to quantum theory, electrons are unlike anything you've ever experienced before, because electrons are neither a particle, so they aren't like a chunk of matter, and they're neither a wave, which is like light. You know, light is light matter? No, light is transmission of energy, you know, is waves. So electrons are very tricky to describe. And so there's a good reason there's no size, because nobody knows what, you know, or, you know, they'll just say it's zero because of this, you know, the recent research from this collider. You've heard of that Hadron, what is it, Hadron Collider? And this whole theory, you know, the things pick up mass from the Biggs, or what was it, the Higgs particle? Higgs particle, right? Picking up mass through space. Well, anyway, let's continue on with this. So all we're going to know is, you know, the charge, which we use, you know, just the integer here, it's a lot easier, and I guess that's about it. We don't have the size. Now, for the protons, you know, we got 1.6 times 10 to the minus 19 coulombs for the charge. This is plus 1 fundamental unit of charge. How about the size of a proton? Is that known? How about the shape of a proton? The size and the shape of the proton, is that like the electron? You know, who knows? You can't even imagine it in a way. Well, that, you know, the size and the shape of the proton, this has been measured, because what does the nucleus of a hydrogen atom consist of? A proton. Right? And the reason they're protons, these are much more massive particles, and so we don't have this problem. Much more massive because they weigh a lot more. This one, we don't use grams, because grams are a terribly inconvenient unit. For the electron, instead of using grams, we use something called the U, or the AMU. And it turns out it's about 0.000548 AMU. Depending on how many sig figs you want to write. So most people just remember it to 1 sig fig, 0005 U. The proton weighs a lot more, about 2,000, you know, 1,850 times more than the electron. And so the proton, most people memorize the mass of the proton, not in grams, but in U. And so when you memorize the mass, it's 1.0087. I didn't memorize that. I just memorized 1.0 U to 2 sig figs. The neutron, sorry, this is getting messy. The neutron is given this symbol here. And the neutrons, these have zero charge, and their mass is 1.0079 U. Or, you know, to 2 sig figs, it's easy to remember, because it's just 73, sorry, 1.0073 U. To 2 sig figs, you should have this memorized. It's 1.0 U. And so most of the mass of the atom lies in the nucleus, and very little mass lies outside. All the positive charge lies in the nucleus. All the negative charge lies outside the nucleus. About how big are atoms in size? Well, atoms are roughly, say, 1 to 5 or 6 angstroms. You know what an angstrom is? An angstrom is 10 to the minus 10 meters. We don't have to use angstroms. We can use picometers. Picometers are probably the closest. So rather than 1 to 5 angstroms, we call this 100 to about 500. Actually, it goes bigger than 500 picometers. But this just gives us an average idea of the size. And so the diameter of atoms, 100 to 500 picometers, or roughly thereabouts. How big is the nucleus? How big is the nucleus? Well, the nucleus is tiny. Well, how tiny is it? And so in Chem 4, they have this analogy. I think it was in Chem 4 where I read this. But if the, I think it goes like this. Some of you might remember it, but it's been a while since I taught it. If the nucleus were a golf ball, then the atom would be a, was it football field? Is that right? And so a nucleus is a golf ball, the atom would be a football field. So in terms of that, well, in terms of the size of the nucleus is about 1/10,000, the size of a, I don't know if that's correct, but for everything, but we just want rough, you know. And so this is about 1/10,000 of the diameter of the atom. Something like that, just something very small. So gold atoms are really dense, right? They got a lot of mass in a small volume. So gold atoms would be extremely dense. But when you look at a gold atom, all the mass is in the, pretty much in the nucleus. That means that, you know, the densities that I gave you, the density for gold is tricky because that's not the density of a gold atom. You know, when I gave you the density of a gold atom, that was, what was the density of a gold atom? I'm sorry, what was it? 20 grams per mil. When I gave you that, that's gold atoms packed together. When you pack together atoms, there's gaps. You know, there's some empty space between the atoms because these are balls, right? These aren't cubes you pack together. And so that empty space has no mass. This is what we call vacuum. There's nothing in there. And so when we measure the density of gold at 20, we're also, you know, counting all this empty space, which we call the void space here and there. If we actually measure the atom, a single atom of gold, it would be a lot more dense because if I just took one of these spheres out and measured its density, it'd be a lot higher because there's no gaps. Does that make sense? And so the density of a gold atom is actually a lot higher than 20. But then I go and I look, well, gold atom is mostly empty space. If I measured the density of a gold nucleus, right? If I measure the density of a gold nucleus, then it would be a lot higher because it's a tiny volume with all the mass. And so for nucleus, for the nuclei, nucleus for multiple, nuclei for single, but for nuclei, is that right? Nuclei for multiple, nucleus for single. For nucleus, the densities are enormous. You're going to have a homework calculation where you're going to calculate the density of a hydrogen nucleus. In other words, a proton. And as I recall, it's been a while since I did the calculation, but as I recall, it comes out to about 20 tons. 20 tons per cubic centimeter. Is that huge? 20 tons per cubic centimeter? Enormous. I mean, 20 tons of matter in a cubic centimeter is just mind-boggling, right? There, you could get a mind-boggling number, and I wouldn't throw it in the garbage. You know, I thought, oh, that makes sense, right? It makes sense because of that. Okay. All right. Anyway, let's continue with this. So, what are atoms made up of? Is there anything else atoms are made up of? Is that it? What about all those things like quarks and bosons and whatever else? What about all those things? Where do those things lie in the atom? You know? So I have three particles, right? I have the proton, the electron, and the neutron. What about the quarks and the bosons and the whatever else? Where should I put those? Well, I told you, in order to understand a proton, the proton's property, then what do you want to know? You want to know what the proton's made out of. What is a proton made out of? Well, a proton's made out of a proton. But, there's some physicists that say, well, a proton is made out of something, right? And then they try to break it up into smaller pieces, protons, neutrons, whatever else. They'll try to break it up into smaller pieces to see what these things are made out of. But for chemists, we aren't breaking up into smaller pieces. Those particles are, derived from breaking these up. For chemists, an atom is made up of three things: protons, neutrons, and electrons, and that's it. Now, the physicists, of course, they want to understand the properties of these, so they're trying to get the composition and structure of these things as well, right? But we aren't. Because what we care about is chemical properties. Chemical properties are physical properties and chemical properties. In other words, the properties of matter, which the definition on the syllabus is slightly different than the way I do it. Okay, I spent too much time with this earlier stuff. Maybe I'll ask you one question about this history stuff. The more important things are this. We want to know about the behavior of, let's pick hydrogen. This is the simplest, right? What does a hydrogen atom consist of? A proton and a electron. And so in the nucleus, we'll have one proton, and out here we'll have one electron. The proton I'll just represent like this. Okay, this is it here. This is called, in other words, we'll write it here. One proton, one electron. If we look at all the hydrogen atoms in nature, it turns out there's another hydrogen atom, too, that consists of a proton, so-called plus here, and a neutron, and an electron. And so this nucleus is a little different than that nucleus. This nucleus also has an additional neutron. And so this is going to weigh a lot more. If a proton weighs 1.0 U and a neutron weighs 1.0 U, then this is going to weigh about 2.0 U. And then throw in an electron, which is just 0005 U. And so this is one proton, one neutron, and one electron. And so what do we call these two hydrogen atoms? Well, these are isotopes. And isotopes are the same element, but different mass, or mass numbers. And my drawings aren't very good here. But having a neutron in there, will it change the size of a hydrogen atom much? What's holding the electron here? The attraction with a proton. Same thing here. And so does hydrogen on the left here, which we'll call hydrogen 1, and hydrogen on the right here, hydrogen 2, do they have the same size or different size? In other words, is hydrogen 2 bigger? You think, true or false? Hydrogen 2 is bigger in terms of size. False. Why? Because, yeah, it's the same number of protons, right? Same number of electrons. Do you expect the properties of hydrogen 1 and hydrogen 2 to be different? Yes. One property is the density. You know, that should be different. Because hydrogen 2 is more heavier. But what about chemical properties? What's the most important interaction in chemistry? Gravity? No, the gravitational force is going to be different. The gravitational force is so weak, it doesn't really matter. It doesn't really impact this. What's the most important thing in chemistry? Force. Electrical forces. Are the electrical forces in hydrogen 1 different than the electrical forces in hydrogen 2? No. Therefore, hydrogen 1 and hydrogen 2 will have the same chemical properties. Therefore, we call it hydrogen, the element hydrogen. And so these two atoms, even though they're different, behave chemically the same. Therefore, they're both called hydrogen atoms. One is called hydrogen 1, the other is called hydrogen 2. These are two isotopes of hydrogen. And you can't tell the difference chemically, but you can tell the difference by density, you know, weight or mass. Right? That's the only difference. It's a physical difference, not a chemical difference. And so isotopes are atoms of the same element. Well, atoms of the same element, what defines an element? The number of protons. Why do the number of protons define an element? Because it's the electrical properties we're interested in chemistry, correct? And so these ones. There's one more isotope of hydrogen. It's called hydrogen 3. Hydrogen 3 has the same chemical properties as hydrogen 1 and hydrogen 2. The same chemical, why? Because it's got the same number of protons, same number of electrons, but hydrogen 3 has 2 neutrons, and so it's a lot heavier, right? But now, you know that nucleus, that nucleus has got a lot more neutrons in it, doesn't it? And it's not the chemical properties that are different. Hydrogen 3 is radioactive because, you know, this nucleus isn't stable. Apparently 2 neutrons is too much for 1 proton. And so that makes this nucleus quite unstable, but that has nothing to do with its chemical properties. The chemical properties of these 3 things are identical. Just one happens to be radioactive and will undergo nuclear reactions. Nuclear reactions are different. It's got to get rid of that extra neutron somehow, or change that. Something else. Okay, but anyway, this is 1 proton, 2 neutrons, 1 electron. How much does it weigh? How much do these atoms weigh? Well, you know what? We know the mass of the proton. We know the mass of the electron, right? The mass of the proton in U is 1.00. 73 U. 1.073 U. The mass of an electron is .0054,858. And to figure out the mass of the hydrogen 1 atom, we just add these together, right? We get 1.0073 sub 54858. These aren't significant digits here. Correct? Okay, how much does a, this one, hydrogen 2 is called deuterium. We'll just give it a different name. Deuterium. It's just H2. Deuterium is very common. You can extract it out of water. How much does deuterium weigh? Well, a proton weighs 1.0073 U. A neutron weighs 1.0087 U. An electron weighs .0054,858 U. And to figure out the mass of a deuterium, we just sum up the masses here. right? And the same thing here. To figure out the mass of tritium, we sum up the masses here. Does that make sense? And so if we want to figure out how much an atom weighs, we just see, hey, what is it made out of? And then just add up the parts. And so here's where you have to know a little bit of nuclear chem. The little bit of nuclear chem that you have to know for this class is called the mass defect. Here, this should work. Here, this does not work. This does not work. Or actually, maybe this does. Necessarily. I should pick a different example. Something that has a more significant mass defect. And the mass defect is this. The mass defect says that the mass of an atom cannot be determined by combining the masses of the protons, neutrons, and electrons. And so the example here, I'm just going to use the homework example. We'll look at the isotope fluorine-19. Do you guys remember these numbers? 19 is called the mass numbers, right? And what symbol is the mass number given? A. The symbol is A. And the mass number is not a mass, right? The mass number does not equal the mass. The mass number is close or approximates the mass. What is the mass number equal to? The mass number is equal to the number of protons plus the number of neutrons, which is approximately the mass of the atom minus the electrons, right? Because a proton weighs about 1 U, the neutron weighs about 1 U. And so this is why it's called the mass number, but it isn't the mass, it's about equal to the mass. Then we have something called Z. Z is called the atomic number. What is the atomic number and why was it omitted here? The atomic number is the number of protons. Well, the number of protons identifies the chemical properties of that, right? The number of protons is going to dictate the electrical interactions, correct? And so the number of protons defines the element. And so the element fluorine has an atomic number of 9, the red number on the periodic table. That means there are 9 protons in fluorine. And so we know the composition of fluorine. The composition of fluorine-19 is this. Fluorine-19 consists of 9 protons, 9 electrons, it's neutral, plus 10 neutrons. That's it. And so if I want to figure out how much a fluorine weighs, I just sum up the masses. If I sum up the masses, the sum of the masses here is greater than the actual mass of fluorine-19. Why? In other words, the sum of the masses here is equal to the actual mass plus the mass defect. In other words, the actual mass of fluorine-19 is a little lighter than what we expect. In other words, we lost some mass. And so mass was lost. And the reason is this. Some of the mass of the nucleus was converted into what we call the nuclear binding energy. The nuclear binding energy, why do we need that? Well, the reason we need that is because we have 9 protons in the nucleus. And we're talking about the nuclear force. Well, the nuclear force converts some of the mass into energy to hold that nucleus together. And so the nuclear binding energy is equal to this delta M. The delta M is the mass defect. It's the lost mass. And so some of the mass of the nucleus was converted into energy using this E equals mc squared, which I think everybody's familiar with from Einstein, right? E equals mc squared. And so this energy results in the energy required to hold that nucleus together in order to overcome the electrical forces trying to rip it apart. Does that make sense? And so let's just do a example of this mass defect by calculation. The actual mass of fluorine-19 can be determined. Do you know how to determine the actual mass of fluorine-19? You weigh it. Can be determined by weighing it. How do you weigh a single atom? Do you have like an atomic size tweezers using 2 STEMs and then just pick it up like some chopsticks and then transfer that single fluorine-19 atom to a balance and drop it on the balance? Is that how you weigh a single atom? No. No, yeah, there's no balance that's going to be that sensitive and that precise to weigh a single atom. Instead, we use an instrument. Do you know how you weigh single atoms? What instrument we use? We use something called a mass spectrometer to weigh single atoms. And what you do with the mass spectrometer is you shoot a whole bunch of fluorine atoms this way. And then you have an electron gun or some other way to charge those. You know? And so we shoot the fluorine atoms, they're neutral. And you get an electron gun hits an electron, knocks an electron off and creates ions, or electron sticks onto the fluorine-19. How do you make an electron gun? You make it like a cathode ray tube, kind of thing, and shoot electrons. And so those charged fluorine atoms are going to be deflected by a magnetic field. And the angle of deflection depends on their mass. And so these are very light atoms here, and these are very heavy atoms here. And in a mass spectrometer, what we do is we calibrate this using an atom with very well-known mass, something like carbon. Carbon's perfect for calibrating the mass spectrometer because do you know what the mass of carbon-12 is? Everybody should know the mass of carbon-12 because do you know what the mass of a carbon-12, a single carbon-12 atom is? All right, think about it, and then, I forgot the break, so let's stop. We're going to take a break and then start again.